Thanks, David. It's a pleasure to be here. Biz is a really exciting space, and I'm happy to present here. So today I'm going to talk about causal. Oh, sorry. Oh, it's on. Oh, all right, good. All right. So I'm going to talk today about causal inference in the age of big data. And by causal inference, what I mean is you're interested in what the effects of some treatment are. The treatment can be a drug. It can be an ad campaign. It can be a persuasion campaign and change people's minds about how they vote and for whom they vote. It could be an education reform. You want to increase test scores. It can be a medical procedure, right? Or it can be an online, it's a change to an online platform, right? So you do some intervention and you want to know what its effect is going to be, right? And when you're interested in this kind of question, this is kind of like the golden age of that question because the data that you get to use is just exploding. Right? And I've done work like in all these areas, right? So like the nicest data that you're now generating, and it's also where the biggest methodological advance currently is. And it's a bit of a lesson there that the biggest advance and the best data is in the place where you observe the least regulation, and that's currently in online platforms. So think Google, Facebook, Amazon, Uber, right? So human activity is just generating tons of data on people and their behavior and things that you can link to experimental manipulation, right? So the other things that are generating this data are the Internet of Things, which is coming, right? So just passive sensors on your fridge, your phone, and whatnot are throwing up data. There's electronic medical records, right? And then there's genomic data linked to electronic medical records. That's really cool. I mean, that's less advanced in terms of the methods we can use and how we can experiment, partly because of data proprietariness, and partly because of regulations that are stopping the latest data science innovations to coming to medicine. I'm going to talk a little bit at the end about that, some policy implications for where the energy is. And there's a lot of just administrative records that the state generates, the government generates, and people can then use, right? I have a graduate student that has, from North Carolina for 15 years, all of the school data at the individual level, criminal justice records at the individual level, and IRS data in the individual level linked. Now, he doesn't have the IRS data on his computer, but other people do the linkage for you, so you can ask questions like, hey, what is the effect of a good teacher not only in your earnings 20 years later, but how does that interact with the criminal justice system, right? So you're just generating just tons and tons of data in an unprecedented way. And the key thing about this data is that not only is there lots of it, so there's lots of rows, but it's very wide. It's very granular, right? You have very detailed information on people. And so much of this data has near census coverage, right? If you think of the online platforms, they have billions of users, right? They have most everybody online, and they have just lots of data on them, right? And that's pretty unique and unprecedented in human history and what we can do with that, right? So with that, with great data, people want to do different things, and they're not happy just with the things they used to do before. And one of the things is the personalization of treatment, right? It's often called personalized medicine or just targeting optimality of treatment. So it'd be like, hey, if I think I have some way of getting people to get out the vote, I just don't want to give everybody the same message. I want to target to the people it's going to be most effective on, right? If I have some drug, I want to target it to the people who are going to benefit the most and it's going to harm the least, right? So I want to do this personalization. Now that personalization is going to lead to other things. Now I can create markets that I couldn't create before, right? Think of ride sharing. Right? It's sort of like, hey, and I can create a market. I can match supply to demand. I might have to charge different prices at different regions to get supply and demand equal in a way that I want, right? And I can use this data to model behavior, right? So I can try to figure out what people are going to do. What the online platforms are doing, for example, is estimating supply and demand curves at scale, like thousands of supply and demand curves a day with randomized experiments. And the estimation has been done by machine learning. So it's sort of like, the idea of estimating supply and demand curves goes back a long way. Instrumental variables created by Wright in the 1920s. And back then, he had to wait for like, oh, well, there's going to be a change in weather, and the weather will change the supply curve, but not the demand curve, and let me use that as an instrument. It's like, no, if you're Uber, Amazon, you just get to generate your instruments at scale because you can change the prices to your suppliers and your customers and observe how the demand and supply curves change. And you do that at scale thousands of times a day to the point that you understand, for example, the supply function of your suppliers better than the companies themselves do, right? Which is kind of funny, right? So for all these cool uses that we're going to do to it, a lot of inferential problems arise that we don't know how to quite deal with. So it's like a big research activity, right? The data is very heterogeneous, right? It's and more data you get, its heterogeneity does not decrease. And this is a bit of a problem from a statistical theoretical point of view. Like one view of most like results in statistics, like the central limit theorem and stuff, is as you get more data, things are stable enough that the problem gets simpler, right? Part of the view is, if you have Facebook, the next 100 million Facebook users will look very different than the current 2 billion, right? As you're getting more data, the heterogeneity is not remaining stable, right? The next 100 million are going to be mostly in India, for example, or the other parts of the developing world. They're not going to obviously be from the US and Europe because you've just exhausted that, right? So there's a heterogeneity in the data and they never decreases. And you've got to be sensitive to that heterogeneity because you want to target your policies based on it, right? And then once you figure out this heterogeneity and how the treatment effects vary, you want to optimize the treatment allocation, which is an algorithmic problem, right? And also regulators and customers often want the results of your systems to be interpretable. Right? So you're asking a lot of hard things because you want to justify what your algorithm does on this vast amounts of data. So there's lots of inferential problems that we got to deal with, and it intersects nicely with both statistics and computer science in complicated ways. Right? So the examples I'm going to talk about here, some are theoretical, and there'll be some data in here, are all on causal inference, and causal inference is very different from the prediction problem. And it's different in important ways. Like a canonical prediction problem is, all right, I got a bunch of images. I need an algorithm to tell me are the images of cats or dogs, right? Now, if in the modern world I can get 1 million images, and if I've exhausted those 1 million, I can get the next 1 million images tagged by cats and dogs, and it's inexhaustible, sort of, right? And there's current features that kind of data has. One is for every image, you know if it's a cat or dog, right? And it's tagged by somebody, so it's just known ground truth. Right? Causal inference doesn't work that way. Say I do an experiment on 100 million people, which we regularly now do, right? And I have 100 million observations, and I've assigned 50 million to treatment and 50 million to control. I'll show you some examples of these. And I estimate the average treatment effect, which I can with pretty high precision, because I have 100 million people. I do not know what the treatment effect for any individual was. I do not know that, right? That has to be inferred. I don't know what ground truth there is, right? So when I'm interested in causal inference and I need to create these machine learning algorithms to try to estimate it, ground truth is not known. I have to estimate it, even in the most ideal case. And those estimates can have less and less noise as I get more and more data, but it makes it a different problem, that the inference step cannot be avoided. It's like always there, right? The other thing that makes it different from the prediction problem is that just because you have more data doesn't mean causal inference is easier. Like all my data examples I'm going to give you are based by randomized experiments. So the randomization is giving you identification of the causal effect. If you didn't have randomization, and people often ask me, hey, Jazz, look, we don't want to do a colonoscopy on all of our patients' electronic medical records. That's kind of expensive. Patients don't like colonoscopies. Can we just go up the transverse colon? Here's some data. And you're like, hey, why did the physicians and patients decide to only go up the transverse colon? And they're like, I don't know. And I'm like, well, it seems like an impossible question to answer then, right? Because the people who only got up the transverse colon are not exchangeable with the people who got the full colonoscopy. I don't know what to do, right? It's going to be a deeply mysterious thing. So more data doesn't solve that fundamental identification problem, right? And then the thing that's kind of related to this, and it's going to come back on the second part of the talk when I'm talking about the personalization and heterogeneity of treatment effects, is that if I just want to predict what you're going to do tomorrow, and I don't know anything about the problem, and usually we don't know much, I can get a pretty good covariate that's going to predict what you're going to do tomorrow. And what I'm going to do is I'm going to measure what you did today and yesterday, right? If I want to know, are you going to buy a book on Amazon tomorrow, I can look at, did you buy a book from Amazon yesterday, right? Or the day before. If I want to know what's your probability of voting for the Republican presidential candidate tomorrow, if I looked at how often you voted the Republican presidential nominee in the past, it's going to give me a pretty good indicator. But if I'm interested in, no, not that, but if I give you some message or try to get you to vote, what covariate is going to predict that treatment's going to be extra effective? Well, that's now, I don't know how to get that covariate. Right? Because it's sort of like, all right, have I run this experiment before? Have you seen that appeal before? I get to use that, right? And if you don't have that, it gets very hard to target, right? And that's not so much a statistical or algorithmic problem. That's just a feature problem of information. Our theory for who's responsive to particular treatments is not very good, right? And you're just not going to passively collect that information. So you can see this in your own online behavior. Because we're not good at this, and online systems aren't good at this, you get the canonical, hey, I just bought a fridge from Amazon, and now I'm getting ads for buying fridges on Amazon, right? So and you get the same thing in presidential campaigns. It's like, hey, let's send someone that abortion rights are important. Oh, who should we send that ad to? Oh, we should send that ad to people who support abortion rights intensely. And we have the scores for every registered voter in the US, but how much we think they support abortion rights, let's target that. It's a little weird, because if you really supported abortion rights and it's really important to you, us telling you it's important isn't going to give you any information, right? That's probably not the optimal place to nudge, right? You probably want to be somewhat below that, right? So you get a whole bunch of inferential problems that don't kind of go away here, right? So, but the data explosion has changed the balance between theory and data. One way of viewing it, which is a little, I've adapted from Leo Breiman's famous essay that I know many of you will know about two cultures, is that whenever you do anything, like with data, there's like two general classes of justifications, right? The first justification is, hey, I have some relevance theory that tells me this is a good thing to do, right? And that's like a canonical statistics justification when it's good. Leo wrote about it in a more negative way. I'm just going to assume the data were generated by some process, and why did I assume that process? Because I can do some theorems. And if I assume a different process, I can't. Right? So hopefully you're not going to do that. That's not particularly good theory, but still there's a theoretical justification. And the other one, which is very much more of a modern thing that you can easily imagine you need a lot more data to do, is like, no, I don't really have any theory, but it works. Right? Google's convolutional net for image classification has 11 layers. Why 11? 10 wasn't enough, was the answer. Right? There's no deep answer to it other than 10 wasn't enough, 11 works better, and we have tons and tons of data to prove that it works better. Right? There's no like a theoretical justification, and none of us question it because it does work better. So you're like, all right, fine. Right? And you don't want to confuse the two. Right? And this discipline has general comments for how time and energy may be invested by society, right? So if we're in a world where data is poor and you can't do this training test validation, maybe you want to invest more in developing theory, right? And as important as theory is, if this gets easier to do, then maybe you want to invest some more on that. It's going to change the marginal return of what you may want to invest in, right? And if you say this to the one part of my life, the data science side, that's not very controversial, right? People nod. Certain departments might not move in that direction, but they all nod. That's true. I can rewrite this slide in a social sciencey way, then it's much more controversial, right? In the social sciencey way would be like, look, if you're sitting there in London in 1817, and you have a choice, you want to start a field of political economy, and you have a choice to sit in your leather chair and think about what should the mechanism of political economy be, or run around trying to collect data from factories and the prices of fish oil and pins and whatnot, the returns of those two kinds of behaviors is going to be something, right? And we know from the literature from like the early 1800s that the investment in sitting in your arm and thinking deep thoughts was way higher, right? Ricardo came up in 1817 with comparative advantage. It was a deep idea. It was a new idea. It was a profound idea. More than a few people still quip that if they could teach our elected officials one new idea, it would be comparative advantage, which is something that's not obvious. They don't get. The current administration doesn't get it, for example, when it comes to trade. But it's not an obvious idea. The previous president, Obama, didn't get it when he wrote his first book. He was young. It was clear. When we talk about trade, it was like comparative advantage was not a concept he got. By the time he was president, he got it. And we talked about trade and immigration in ways that were consistent with it. And we don't read any of the work generated in the early 1800s that was data-oriented, because the data was terrible, right? But now that the data is much better, you might change the allocation decision some, right? And stated that way, it's now much more controversial, especially because what's going on is, I would say that the social science and humanities side of campus is far, far more conservative than the other side of campus. By conservative, I mean small c conservative, right? So the data deluge, as a society, we're going to invest a lot more in this than we used to, in the testing and validation. How that plays out in which departments and which side of campus, we'll see, right? So the fact that these two things shouldn't be mixed, even though they're mixed terribly in the academic literature, in corporations and elsewhere, you go talk to a team, you go, why are you doing this? And they think, we have really good theory. I start talking about theory, they go, oh shit, he knows about theory. No, we have really good data, right? And you start talking about the data, they switch back to theory, right? You don't want to be confused, and people are usually pretty confused. It's true in academic literatures. It's true in actual use cases. It's not a new thing that you need to be clear about this. Finetti, in his famous book on probability in the 70s, bemoans this. He was bemoaning that, oh, people are too quick to think that a central limit theorem kicks in all the time, and random variables have to be normally distributed, and he's very irritated by this, and he says it's obviously not true, and he quotes Poincare lamenting, everyone believes in the normal distribution, experimentals believe in it, that it is a mathematical theorem, and mathematicians believe that it's an empirical fact, right? And you do not want to get confused, and so much academic literature, whether it's in statistics or economics, political science, is deeply confused about what we do. What's the evidentiary basis? And you want to be clear. And the new data thing has kind of changed what the evidentiary basis is going to be. Right? Even like stick with the example of the normal distribution. When I was in graduate school and someone told, and you said, hey, I have independently generated data, and I have 1,000 observations, is the normal distribution and a good approximation? And you're just taught, yes, just assume it's going to be good, it's going to be great. And your outcome is bounded, right? So the regularity assumptions will be kind of mad. It's not like you have finite third, fourth moments, et cetera, et cetera. But now with online platforms, it's not a theoretical question. You can just go look, right? So we have population data from online platforms. So many of them have discovered that if you have a sample size of 1,000 and you want to know what the population mean is for some metric, and you sample 1,000 people, your coverage does not follow the normal distribution at all, right? And you just know for what metrics it does and what metrics it doesn't, and it's not like and it's just a thing. And the reason is, even for bounded metrics, they're often very skewed and kurtotic, right? If you take, like, for many a metric, the interquartile range is 0. So the 75th to the 25th to 75th percentile is 0. If I look at the 100th percentile minus the 99th percentile divided by the 99th minus the 50th, that ratio can often be more than 10,000, just because of tons of zeros. Just think about ads, right? If I have an online ad, the median person doesn't click it. The median person who clicks the ad buys nothing, right? And all the action is in the upper tail, right? And this example is not theoretically that disturbing, because if someone said, hey, I have 1,000 observations and most of them are zeros, then you know you don't actually have 1,000. But you can go test this thing. You can also then test, you can also go validate things in a different way. So this figure is based on over 2 billion human beings. Right? So what this figure is based on is about 250 different experiments. Each experiment has a sample size of 100 million people, right? And then you have a couple hundred different outcome metrics, and what you're looking at is different subgroups. What this is is a random sample from an experimental platform for a large internet firm, right? So there's no p-hacking here in the sense that every analysis done by the engineers is recorded, right? There's no publication bias. There's no what they decide to report. You just get everything. You take a random sample of all their queries. Because you want to know, how do treatment effects go? What's the distribution of treatment effects in this universe for this firm, right? So at the end, so some of these are just like the average of treatment minus control. Some of these is, so give me the treatment effect for women. Give me the treatment effect for men. Give me the treatment effect for iPhone users. Give me the treatment effect for people 18 to 25 who are green, right? Overall, this figure is plotting 25,000 different treatment effect estimates, each one of them powered on average with a sample size of 10 million people. And that's what the empirical distribution looks like. So most treatment effects are 0, and the distribution around it is not normal. It's Laplacian. It's like double exponential on either side, right? And when you see data like that, lots of debates stop, right? Usually, you go in, there's Bayesian. Should we use a prior? Some of us, like me, don't want to use a prior, so we end up having this circular fight. When you have database like this, we don't have those discussions. It's much easier to say, hey, look, we have a prior. Where's the prior come from? These 2 billion observations. Should we burn them and not use them? No, we probably should use them somehow, right? There's no, right? So data has a habit of just cleansing a lot of otherwise ideological battles we would have about how to do estimation. And this is going to come up again, because if you have problems like this, you know that most treatment effects are 0, and there's very tight spread around that. You might want to use that in the estimation stage later, right? So part of what ends up happening with large data, and you could sort of see it on the other side, is that you end up being very interested in small treatment effects. As a data science group in the Valley, I had mugs with this. It goes, with great power comes small effect sizes, right? And one view is look, if I have some treatment that increases turnout by 0.001%, or increases the energy usage of, on your server's 0.001%, you may not care about that if you have 10 users, right? But if you can roll that treatment out to 100 million people, all of a sudden you start caring about an increase in turnout of 0.001% or increased energy use of that, right? So you become very interested in small treatment effects. So part of what that ends up doing is that even though you have these vast experiments and you have tons of data, you still are very hungry for power. You're very hungry for precision, right? The small things are the difference between something being useful or not, right? So at the same time, you're very worried about people digging through the data and doing all sorts of weird analysis, right? In the sense that, you know, you can easy to run 1,000 different models, report the one that works. So statisticians for 100 years have had pretty standard ways of dealing with it, right? The oldest way we know, if I have a randomized experiment and I want to get some extra power to get covariate adjustments, to say I'm going to block. What is that is, oh, I'm going to compare men to men, women to women, tall people to tall people, people with the same education class, so on and so forth, and within those subgroups randomize. And then take the weighted average across those groups. And if I do that, and those covariates that I grouped you in are predictive of outcomes, then I increase the precision of my estimator, right? And that's called blocking, and I can do that after randomization, and that's called post-stratification. And we've been doing this for at least 100 years, and it's great. And the only problem is we prove it's an NP-hard problem, right? And I started thinking about this problem when a former grad student of mine, Erin Hartman, in 2012 was working for the Obama campaign. She was the head of all polling, and she goes, hey, Jazz, I got to do these large-scale experiments. I don't want these pollsters at the end to do some weird analysis on the data. I need something that will work. And oh yeah, it has to work on arc-ready servers. And you're like, none of the usual things will work, right? Because their polynomial time is not going to be good enough for them because it's still too high because they have like, you know, these experiments in the tens of millions. So you need something that's much, much quicker. I never got something to her quick enough, but eventually we wrote a set of papers. And there's a set of papers that, you know, when you're starting out in grad school, you probably don't think you're going to end up writing, right? Because it ends up sounding very operations researchy CS-like, right? Because you're like, all right, what I got to do is I got to group data together, block them, cluster them, and really fast. And what we have is n log n time, so it's near linear time and linear space complexity. At first, you're thinking this got to be a solved problem in CS, and it turns out it wasn't. And you kind of like use some ideas from operations research, and it's turning into a bottleneck subgraph problem, and you can do some proofs for the algorithm. And the thing that makes it interesting is all of your main statistical properties are coming from the randomization. The randomization is controlling the rate at which your estimator is converging, which is square root of n. It's controlling your minimax risk. So all you want from the algorithmic side is just some extra power, right? So what we can prove is that if you want to cluster the data and you want to look at the distances between any pairs of observations within the cluster, consider that the maximum pairwise distance. If an oracle could cluster the data, the maximum pairwise distance would be lambda, right? And you can prove that that process, an NP-hard process, you're not going to like do this quickly, but an approximation algorithms will exist. A polynomial time approximation algorithm will exist that will do 2 times lambda. Now, polynomial time is not good enough, right? So you're like, all right, I'm going to give you even more. You know, a CS person would have written the paper as, I prove that no polynomial time algorithm exists. It's better than 2 lambda. So here's my 2 lambda algorithm, and call it a day. But I know that's not going to work in practice. So then you work a little harder, and you go, hey, look, no, we can get an approximation algorithm that's 4 lambda. So it's even worse, but it's n log n. So it's really fast. So people can actually like use it. And you get this thing on a computing budget. Your properties are coming from the randomization. You don't have to have the algorithm doing such a great job in grouping people because it's only making it better, right? It's all about the constants, not the rates, right? And since it's like a CSE thing, you got to show plots where yours is n log n and the other ones aren't. So those are those plots, right? But the high idea here is that there's a whole bunch that the standard with big data, what makes causal inference hard for one set of problems is that the usual things we know how to do, we've known how to do for 100 years, they don't scale. So you got to do some work making them scale, right? But you don't stop there, because human beings being human beings, now they have vast amounts of data. They're not interested in simple problems. They're not interested in the difference of means anymore, right? They're interested in harder problems, right? So with the thing that's in vogue these days is personalization, right? There's not a whole lot of math in this talk, but I'll have some notation. So one way of thinking of personalization is for every individual d sub I, individual I is d, has a treatment effect, and that's my outcome if I were given treatment minus my outcome if I was given control, right? So I'm going to knock on Jane's house and ask her to vote, or I'm not going to knock on Jane's house. And the difference between the two is your individual level treatment effect, right? And that's what we're interested in. If you're the patient, you want to know whether you should take this drug, that's what you're interested in. The only problem is this is incredibly difficult to estimate, right? Randomization is not enough. You have to say things like, oh, I'm going to knock on Jane's door, ask her to go to vote. I'll observe whether she votes or not. Next election, I won't knock on Jane's door, and I'll see if she votes, and I'll make an assumption the fact that I did one treatment before the other doesn't affect your behavior in the future, which seems strong, right? So this is generally very hard. Online platforms can kind of do this. Think of Amazon for Prime, think of the Facebook newsfeed algorithms. They see you repeatedly, but they have to make these assumptions about how these treatments interact over time. So what people usually do is not estimate this, they estimate the conditional average treatment effect. Even in papers that say that they're estimating this, they actually do this. And no disrespect to my CS friends, that's a field that particularly says papers title as individual treatment effects. What they actually do is estimate that, right? So what is this? What this says, okay, I can't really estimate the treatment effect for jazz because there's only one jazz, but maybe when I'm making the allocation decision for jazz, I'm going to estimate the treatment effect for men. And jazz is a man, I'll give him that treatment if the treatment effect for men differs from women, right? So it's just going to be the treatment effect given some strata of X, and it could be men or women, X could be continuous, so on and so forth. It turns out, and it's worth noting, it's kind of like an obvious thing, but it's often missed in both the academic literature and in use, that if I look at the error of this conditional average treatment effect, which is what everyone goes off and estimates, and the error that it's going to make in making predictions for me, some part of that error will never go down. It's not a function of n. So what's going to happen is one part of this error is estimation error, which is if the X is just men versus women, right, it's going to be what's the treatment effect for a man, right, and my estimate of the treatment effect for a man. And that's going to go down at square root of n, right? And so this is going to get smaller and smaller with n. But there's another part of the error that's not a function of the n. And that's the error that's how different am I from the average man? That doesn't go down no matter how much data you have. That's just there, right? And it just turns out you can make an information theoretic claim about how much extra data in terms of n helps you. And it turns out it doesn't help you very much in terms of expected risk. If I want to get expected risk down and giving me the best optimal treatment, more n doesn't really help. What helps is more covariates that are informative, right? So if, these vast experiments would not be that helpful unless those features are very predictive, right? And this now has implications for online systems when you ask for privacy, when you ask them not to use your data, right? 2 billion observations does not help them target unless they use your covariates. Right? It's just like a thing. 2 billion is not that useful. And the information theoretic way of kind of arguing about it is if I don't have any covariates and I have 1 billion observations versus just one to target something to you, I'm only going to do 4 times better, even though I have 1 billion observations instead of 1. Right? That's not going to give you much gains. Right? So we're going to target this thing. So give you an example. Right? So these are public. Part of what's happening to the data is with all this data explosion, most of the interesting data now is not public. Right? This last election, a lot of the coolest experiments we have are non-public. This is a public experiment, which drove a lot of the work private, actually. This experiment that many of you will know comes from Gerber, Green, and Lemire that we reanalyze. So what ends up happening in the US is for whom you vote is obviously private. Whether you vote or not is a matter of public record. Right? So you can go to firms and just get the voter files for the entire country that have a history for whether you voted or not, and if you move, they try to merge whether you moved, and you can get a record of that. So what they did in a very clever way is sent a postcard out, and the postcard's kind of creepy, right? The postcard goes, what if your neighbors knew whether you voted or not? And they go, so please vote. Some people failed to vote, and then they have your name and your neighbors' names, right? And they go, in the past, whether you voted or not, a blank for the election, which was August 6th, and said, we're going to send you a new postcard. Please vote. It was hugely successful. This postcard was super cheap, increased turnout by 8%, which is massive treatment effect. You can imagine once that paper's published, so much of the research goes private, right? Because now lots of money comes rushing in to try to use this because you're going to optimize. You don't want everyone's turnout to go up. You want just turnout of your supporters to go up, right? So you start optimizing and targeting. And in this experiment, they had 5 different treatments, right? To give you a hint from where the literature, where the field has gone after the 3rd presidential debate in this last cycle, the Trump campaign online did 100,000 different treatments, over 100,000 different treatments to find the optimal treatment allocated for different subgroups, right? So part of what they ended up finding, for example, is for African Americans in the upper Midwest, you basically just run Bernie Sanders ads without the Bernie Sanders part in, talking about super predators and stuff, which were completely, they're just factual ads targeting that subgroup. Probably targeting for their turnout to decrease, not thinking they're going to vote for Trump. Right, so if I do this, what do I want to do? Where do I want to get to, right? I want to get to some heterogeneous treatment effect. I want to know, on average, I have an 8% effect on treatment. I want to know for whom is it effective. So there's a couple of ways of doing it. Of seeing, at the end, you're going to end up with a density like this. This experiment I just showed you has about 200,000 people in control and 30,000 people in treatment, right? And although on average, as an 8% treatment effect, there's quite a bit of spread. This is the scale here is 0, didn't vote, 1, you voted. And you note that the subgroup here is the ones that have a significant treatment effect. There's some evidence of a backlash. So you want to target these people, right? Another way of representing it is what's the treatment effect that varies by your past voting history. So how many times in the past did you vote, right? And the effect appears to be highest for people who have some voting history. But they don't always vote, and they never vote. So you want to go target. Them, right? So then, what do you do? How do we do this? So this is where ML meets the causal inference, right? So the identification is coming from a randomized experiment, but now you're asking a lot from the experiment, right? Because you want to estimate how your causal effects vary, and you're not going to want to make assumptions about linearity or anything else. You're going to want to do something far more flexible. So what we do is we create a method that will use whatever base learner you want to do the estimation. It could be random forest, which is what we use. Bayesian random forest is what we use. Any other ML thing. The minute this paper hit archive, we had emails and calls from 3 or 4 different groups doing deep learning on it now, because that's what we do these days. But we don't care, right? So the theory's at a level above this. The use is a level above whatever your favorite estimator is. It combines a whole bunch of different estimators, right? The key thing I want to get to here is it ends up looking very complicated, right? And partly because you want to be very adaptive to the data and its heterogeneity, right? So if I want to estimate this the conditional average treatment effect, what's the historical way of doing it? There's 2 very common ways of doing it in literature that go back a very long time. The first thing is if I want to know what the treatment effect is, what is the effect of conditional on X for treated minus control, I can decompose this under randomization into 2 different problems, 2 different regression problems. One is what's the expectation under treatment given X, and the expectation under control given X. And I can go estimate those 2 separately, right? And which is the oldest thing. The oldest thing you do is you take your treatment and control group, you split it, you run regression separately, and then you just diff it at X, and you get your treatment effect estimate, right? The other thing you can do, which is the second oldest thing to do, is you run regression and whatever regression method you want, and you just put treatment in as any other indicator, and let it figure out which covariates to keep. Maybe you want to use the lasso. Maybe you want to be foolish and maximize R squared. Maybe you use BICA. So you can do whatever you want to do variable selection, and then you just query the model at treatment minus control and look at the difference, right? What should be obvious intuitively is if treatment has no effect, or it's just an additive effect, not splitting the data up is going to be way better than splitting the data up, right? Because if I split the data up and treatment literally had no effect, and note the previous density, most treatments have no effect, this is going to be less efficient in finite samples than this one that pools data, right? So you want something that does the splitting but also the pooling, right? Because if treatment is very heterogeneous and has a very strong effect, then this thing that pools the data is going to be not as good as the other things. So you want something that's very adaptive, far more adaptive than what you had before, right? And the other thing you want it to be sensitive to is with these modern online systems, and much like the get out the vote thing, your control group is usually much bigger than the treated group. In the example I gave you, had 200,000 controls and about 30,000 treated, right? You know, if you're doing like an experiment in an online system, you have 10 million treated, it is easy to get 200 million controls or 1 billion controls, right? You just go do it, and if you can do it, you want to use that, right? So the idea is that, all right, if you had these kind of data, and the blues are treated, and the reds are controls, and you were asked to estimate models separately, and that's the data you had, well, what are you going to do? Well, there's not a lot of data up for treated. You'd probably fit a linear line. For the controls, there looks like a kind of a step function, so you'd probably put in a step function. So you'd probably estimate that. That'd be the kind of the reasonable thing to estimate. And then when you took the difference to estimate the conditional treatment effect, you're going to end up with a very complicated function, right? Which is kind of goofy, right? Because the whole reason you started for the treatment just putting in a linear line is because you didn't have a lot of data, right? But now, if you did it and you took the difference, you end up this. So what you want is an estimator that's just going to give you what's the right answer in this case, which is just a linear treatment effect. So what you end up doing is something quite complicated. What you end up doing is, okay, right. So the first thing to observe is that if you were treated, I don't have to impute your treated outcome. I observe what happens to you when treated. I just have to impute your control outcome if you were treated. So what do? If you're treated, right, I estimate a model in controls. And remember, there's tons of controls. The data example is 200,000 controls. So I can estimate that model well. And what I do is I take your X covariates for the treated observation and put them in my model of controls, get the output from it, and take the difference. And that's my imputed individual treatment effect, right? And then I can run another estimator to estimate the conditional average treatment effect, right? Then I regress these imputed ITEs on my X covariates, right? And if I think that the conditional average treatment effect is sparse or something, I can put that there. Now, it's more complicated than that because we could go the other way, right? This is just what I did in algorithmic form, right? So this is I'm estimating my model for controls. I'm estimating my imputed individual treatment effects, and now I'm estimating my conditional treatment effect. But I could go the other way. For everybody in controls, I don't need to impute your control outcome. I observe it. I just have to impute your treated outcome. So I can go the other way, right? And now I have two different estimators of the conditional average treatment effect, right? That I can combine in some way by some function of g of x, right? So the estimators here are my model for controls, my models for treated, my model for conditional average treatment effect there, my model for conditional average treatment effect, and my model for how I group the data, right? And oh, by the way, I've told you can like go off and estimate these individual estimators could be lots of different things. It could be king nearest neighbors, it could be random forest, it could be whatever you'd like. So we do theory for this, and I see two of my co-authors here. I see Soren Vinyu and Peter Bickel, who's not here. We do theory on this, right? So we can prove mini-max rates under very special conditions, right? And I'm not going to like talk about the theory, but if it were just left with the theory, we wouldn't be like so happy with the estimator, right? Because the real argument for the estimator is it's very adapted to the data to generate the theory. You have to do it for very special estimators. You can't do it in general. You have to do things like saying, hey, I'm going to assume some smoothness conditions on the base learners. I'm going to assume that this function is, say, linear. And then I can make some assumptions about the worst case error in the first, how it projects to the second, and make some claims, I'm going to hit the parametric rate. That's so and some other things, right? That's not that interesting, right? It's kind of interesting. It's in the paper. It's you do it. What really makes us kind of like it is both in public data and private data, it works well when you have a good idea of what ground truth may be, right? So what you can do now, which I couldn't do when I was in graduate school, is you can get that get out the vote experiment. Remember, it has about 230,000 observations, and you can say, and it doesn't have that many covariates, and you can say, I'm going to estimate on that data the conditional average treatment effect, say using that T model that separates out. The base learner used here is random forests, right? And you just assume that's the truth now. Because remember, for causal inference, I don't know what ground truth is. So I just assume that the model that's not my model is ground truth, and then I sample from that model. And I'm sampling at 10,000, 20,000, 30,000, right? This is the true model. This X complicated thing still beats it, even though that's the model that you assume to be the truth, right? And you can do this in data set after data set, and example after example to try to get some idea of its performance, right? And it's about the closest you can get to like having ground truth, and and you're just not going to work unless you have vast amounts of data, which we do in this case, right? So yeah, and then I'm going to skip these. Just to say that if you have small amounts of data, this doesn't work, right? I'm running out of time, So the little things, I'll put my social science hat on, and I will say that part of what's going on, especially in a space like bids, and it's part of like what's driving me to different kinds of fields and topics, is that the energy here is really in those places where there's the least regulation, that companies have kind of an algorithmic pass. A lot of people bemoan it, that when Facebook's newsfeed algorithm does something, if it's an algorithm, regulators in society gives it a pass that it may not if it were people, right? The flip side of it is it gets to innovate in particular ways that other people don't. Like take ride sharing, right? Estimates from in the academic literature of the social welfare benefits of Uber and Lyft are like astronomical, like massive welfare increases, right? In terms of they created markets that didn't exist before, right? Total amount of ride sharing revenue is an order of magnitude above what taxis were, right? So that has lower environmental costs, there's social benefits going up, but it took an algorithm to disrupt a monopoly the government had created with medallions, right? The monopoly probably should have been disrupted. It's glad it got disrupted, right? In places where you don't get an algorithmic pass, that the VC money can't come in, people like us can't come in and just roll experiments, you see way less innovation, and this is like happening, say, in healthcare, right? The algorithmic revolution hasn't come to healthcare the way that we all thought it would by now, right? And that's like kind of a bad thing that we should be aware of. And I guess I'll stop with, this is our estimate of our productivity numbers, right, over time. They're kind of crappy, right? So my view is you kind of need to not stop the data science revolution, the algorithmic innovation, because if our productivity numbers look like that instead of how they did until the century that ended about 1970, I think our political problems are going to like kind of continue, right? So it's not like we're in a world of great productivity growth and economic growth, and we got to regulate it. We're in a world of our economic growth is not high across the Western world. Our productivity growth is not high. There's been this technological innovation, but it hasn't worked its way through societies and markets. And so part of my nudge is counter to some of the discussions that go on in bids. I think we need to help encourage those transformations instead of slowing them down. All right, so I'll stop there.